Attending the first championship conference, I'd like to welcome to the Chezzy Controls and Stuff session presented by Jared, Tom, and Austin. We ask that you practice gracious professionalism and please turn off or silence your cell phone and other electronic devices. This session is scheduled to last for 1 hour, and if the discussion lasts for more than that time, then the presenters will be available in the hallway after their presentation. Please help me welcome Jared, Austin, and Tom.
Hi, welcome to Motion Planning and Control at FRC. I'm Jared, that's Tom, and that's Austin. For the next hour we're going to be talking and hopefully having a little bit of a discussion about motion planning and control as it relates to FIRST. All three of us are heavily involved in this aspect of the technical side of the FRC program. And this is our first time giving a presentation like this to an audience here at the championship. So hopefully, if we do our jobs right, you'll see some useful stuff that you can apply to your robots going forward. You'll see some stuff that hopefully will make some sense to you, and we'll try to point at the intuition behind why we do certain things. You might also see some things that you don't quite grasp maybe all the math behind them. We try to make sure this isn't a math-heavy presentation, but hopefully if we do our jobs right, you'll be interested enough to go off and learn more about that on your own, or in college, or in industry. So why are we here? Well, it's because robots should move less like the Roomba right there that's driving into the walls. Note that the cat on top of it is actually a very sophisticated motion control system, but the Roomba itself is fairly simplistic.
So good.
And more like that. Those robots at the bottom are the Google Robotics Spot robots. I work at Google Robotics, and they're obviously doing some pretty complex things. That video that's GIF is taken from came out a few weeks ago. I'm sure a lot of people in this room have seen it. It features, among other things, the quadruped robots running through rough terrain, getting kicked by mean-spirited engineers. And actually that video inspired a Belgian grad student to start producing these t-shirts. Stop robot abuse. But anyway, so a little bit about us before we dive in. Like I said, my name is Jared. I work at Google. I work on robots for a living, which is awesome, because I get to play with robots at work and then go to work with the FIRST team and play with some more robots. Tom, want to say a few words about yourself?
I'm Tom Bottiglieri. I've been involved with FRC since 2002. I started out like a high school student, like many of you, on Team 195 in Connecticut, and since then I've gone to college. I got a degree in computer engineering and computer science from Northeastern, and now I live out in California with these guys, and I do web programming as my day job, but I love working on robots, on the nights and weekends. So that's why I'm here. This is Austin.
Hi, I'm Austin Chu. I've been on Team 971 since 2004. I've been mentoring the team ever since I graduated. And I studied computer science at college and controls, and now working at a little startup in Silicon Valley, working on truck control software.
Yeah. And I actually forgot to mention my first history. I was with Team 341 Miss Daisy from 2001 until 2013, and then I moved to California and joined the Boost. So, why are we here for real? So control systems are really fun. All of us up here feel this way, that the most fun that you have in the first season is week 5, week 6 of build season, sometimes your first competition. When you power up the robot for the first time and you want it to do something awesome. You want it to shoot a ball, shoot a frisbee, pick something up, place something. And usually when you turn the robot on for the first time, it doesn't work all that great, because there may be some mechanical problems that need to be ironed out. Your robot probably has very little automation. You're trying to teleoperate everything. And as you add in the automation, the inspiration and the wow factor and the effectiveness of your robot just goes up. And we're going to talk a little bit today about some of these techniques that you can use to automate certain functions of your robot. Software and control is a really hard problem and a really large discipline. I work with a team of people with PhDs in robot navigation and control and planning, and there's a lot of unsolved problems there. A lot of the things that you do in FIRST are actually very, very similar to really hard problems in industry and in academia. So some of the techniques we'll talk about today are, you would not be out of place whether you're looking at a KUKA or a FANUC arm or an industrial mobile robot base. Like I said, I mean, for us on Team 254 and on 971, we're very competitive, and we like to win and yield an effective robot. So adding automation, in our minds, is a way to make your robot better. There's a lot of ways to sort of go off on a tangent and automate your robot, but if it's not focused at achieving a certain goal, you might have something that might be technically awesome, but it is going to be lacking come competition season. So some motivating examples of the sort of things we're going to talk about. So this is a video of the finals in Einstein last year. And that's the 254 robot right there in the middle with the 3 balls. And this is a match against Team 1114 on the far left. And they have their Kinect-controlled goalie pole. And for this auto mode, we know we're going to face a really effective goalie. So we had a spline following drive technique that drove that little S-curve motion right into the corner in front of a goal and was able to score past the goalie. And I remember the dome cheering wildly because most people there hadn't seen this. I think we unveiled it once in a practice match in Waterloo, but that was it. It's probably good. And so we'll talk a little bit about how we did that.
Makes no sense. I can't scroll.
Robots are easy compared to audio visually.
So in this one, so on this robot, the top and the bottom of the claw are mechanically independent. So they're two joints just on the same axle. The only thing preventing the robot from dropping the ball is the control system in the middle. So we spent a lot of time. Well, one of the things we were able to do with that is we were able to get the claw to pack in better and to move more flexibly. But that took a lot of controls in order to make that happen and make it so we didn't drop the ball. And when we initially started, we had bugs, whereas we would do long moves, the claws would separate and drop it.
So we'll talk about driving, we'll talk about coordinated mechanisms, and then also it's been a couple years since this was a big part of the game, but in 2012 and 2013 there was a vision tracking aspect to the game. And here's a video from the Boston Regional in 2012 where the 2 robots at the center, Team 341 and Team 233, both go to that center bridge to try to get extra balls. And then they both need to engage their automated vision targeting system to try to reacquire the goal after they've made contact with each other. So both teams here use the camera-driven feedback loop to try to zero in on the goal and adjust the yaw of either their robot base or the mechanism with their shooter on it. So we'll talk a little bit about how to do this effectively, because this one is particularly tricky because USB web or Ethernet webcams do not make great feedback sensors. All right, so let's just talk in generalities for a moment. The diagram up on the right is one that I'm going to come back to a few times, and you sort of need to squint at it the right way for it to make sense. But let's say that blue circle on the left that says 254, let's say that represents the actual state of your robot. So imagine that's a top-down view of your robot drive base. Your robot's a circle. The circle to the right that says goal in gray, that's where you want your robot to be, right? So in this case, it's 10 feet away in a straight line. So how might we do this? So the first approach we could try is dead reckoning. So dead reckoning, let's say we know it's 10 feet away. We know if I tell my robot to go full speed, it'll go 5 feet per second. It's a little slow for a 254 robot, but for the sake of the math, let's say it goes 5 feet a second. 10 feet divided by 5 feet per second equals 2.0 seconds. So I'll just tell the drive to go at full speed for 2 seconds, and then we'll be at the goal. What could possibly go wrong? Anybody that's tried this on their robot knows that you'll never have the robot do the same thing twice if you do this. There's a lot of variables here that you're not measuring and you're not controlling. Battery voltage, wear on your wheels, subtle imperfections in the carpet. All these things are going to make it so that your robot almost never goes exactly 10 feet. You might get it to go there once, but never again. So let's try using a sensor, right? So Andymark and Vex and US Digital, they sell these wheel encoders. You put one right on your drive wheels that'll measure the revolutions. You can measure your progress towards the goal. You can measure, when you've gone 10 feet. So it's the simplest thing we can do with that sensor that'll possibly work. Well, there's something called bang-bang control. So bang-bang control basically means I'm either going to go full speed one way, full speed the other way, or stop. So we can imagine a control loop that's something like, while true, I'll introduce this concept called error. So error means what's the difference between where my goal is and where I am currently. So when we turn a robot on, we're 10 feet away. We'll check that error. If the error is greater than 0, if the goal is a positive distance away, well then we'll drive at full speed. And if error is less than 0, it's behind us, then we'll drive at negative full speed. And if it's exactly 0.0000, then we'll stop. There's a few problems with this code, right? So one problem is, what do you think the likelihood is that you'll ever have an error of 0.0000? The likelihood is 0.0, yeah, exactly. Well done. Yeah, so if you're going to use this control and you ever want to stop, you need some sort of hysteresis in there, right? So this is what your thermostat does. It has a deadband around your set point. So if you want the room to be 72 degrees, it'll probably turn on the thermostat at something like 70. It'll turn off at something like 74. And this way, it's not constantly oscillating on and off and thrashing back and forth. This thrashing is it wastes time. It's also very tough on a lot of mechanical systems. Telling a gearbox to reverse direction back and forth over and over again is asking a lot out of a gearbox. It can be done in certain cases, but it's asking a lot in general. So the next thing that we are going to talk about is something that I think a lot of people in this room have at least heard of, and this is PID control. So PID stands for proportional integral derivative. Don't worry if you don't know what those terms mean, I'll try to explain. But the basic concept is, well, with bang bang, if I go full speed the whole time while I'm not at the goal yet, well, I'm going to shoot right past that goal, and then I'm going to have to come back, and then I'm going to have to go forward and back and forth. So let's try slowing down when we're near the goal. So maybe we'll command an output to our motors that's proportional to my error. So when I'm 10 feet away, maybe I'm going full speed, but by the time I'm only a foot away, maybe I only want to be going 10% speed so that I can gradually coast down to meet the goal. And it turns out that this proportional controller works in a lot of situations, but there's a couple problems with it. So one, some people who have tried teleoperating their robot drive have probably noticed that when you push the stick forward just a little bit, the robot doesn't move at 1 millimeter per second. It sort of makes a noise and doesn't move until you give it just enough power to overcome static friction or stiction. So friction is a problem with this sort of controller, because you'll be commanding a very high velocity when you're far away, but as you get close to the goal, you'll eventually pass some point where the friction is going to keep you from moving any further. So you're going to be permanently stuck like 3 inches from your goal. So one way to deal with this is the integral term. So the integral term, the I term, is basically keeping a running sum of this error over time, so that if you have a very small error, but you have that error for a long period of time, it'll grow and apply a little bit extra power. So this deals with that, what we call steady state error that comes about because of friction in the system, or other things like friction. Now, P and I together are, there's a lot of PI controllers in the world, but one more problem with the PI controller is you tend to oscillate the goal still, even though you're going slower when you're near it. And the integral is a big reason for this, because you're maintaining the sum of past error. So, you build up your integral term, you then advance the rest of the way to the goal, but you still have some integral error, so you advance past it a little bit, and then you're back to where you were with bang bang. So the very last thing that the D in PID is this damping term, or derivative term that provides damping to the system. So this basically means if your rate of change of error is changing very rapidly, well, then you need to let off the gas a little bit. Likewise, if the error is growing, well, then you need to push a little harder. So it turns out the P, I, and D controller works great for linear systems of first and sometimes second order. Don't worry about what that means necessarily quite yet, but it works great in a lot of situations. But it has some shortcomings, right? I'll talk a little bit about what those shortcomings are in a moment. But first I want to introduce a concept called motion profiling. So motion profiling is a different way of looking at this problem, right? Instead of telling your robot, I'm currently at 0 and I want to be at 10 feet away instantaneously, well, you know that the robot drive can't do that. It can't in 1 microsecond jump 10 feet. It has a maximum velocity and it probably has a maximum acceleration too. And in reality, your robot's going to drive this profile over time. And it turns out if you actually explicitly specify what this profile should look like, it has a lot of really nice properties, including making tuning your gains a lot easier and allowing you to do things like preventing slipping wheels, synchronizing mechanisms. So we're going to spend a large portion of this talk actually talking about how exactly we can do motion profiling in a way that hopefully will make some sense to you. So the graphic here, just so you get some context, is showing the line plot of the position, velocity, acceleration, and jerk of the robot trajectory over time. If you haven't heard of jerk, that's basically the time derivative of acceleration. So it is the same relationship to acceleration as acceleration does to velocity and velocity does to position. So the idea is we want to slowly accelerate at the beginning, where you see the red velocity curve sort of ramp up. Then we'll hit our max velocity and we'll cruise at that max velocity for a while. And then when we're near the goal, rather than just relying on the PID controller, we'll actually ramp that down and try to follow a profile that brings us smoothly to our goal. And these profiles have, like I said, a lot of really nice properties. One of which is at any point in time, you know exactly where your system should be, so it's easy to tell if something's gone awry. Another one is you notice all these curves, the position, velocity, acceleration curves are smooth or at least continuous. This means that your motors aren't thrashing back and forth. They're always being smoothly guided. And it turns out that being smooth is a very important thing in robotics. It has to do with repeatability. It gets into the life of your mechanism. I know in industrial arms, this is really important because they're expected to manufacture, a full BMW every 4 seconds or whatever it is. And they need, downtime on their robot arm. It costs them real money. So this is the technique that a lot of people use in industry for doing this sort of thing. So before I talk about the motion profiling and path planning aspect of all this, I just want to real quick introduce some definitions and clarify some terminology. So on the left you have a path. So path is a sequence of configurations that you want to move your mechanism through. There's no timing information. This is like waypoints. I want to be here, then here, then here, then here. These are all the intermediate points that I want to hit. So path is just spatial, you can think of it. A trajectory has timing information attached to it. So a trajectory has time and therefore it also has velocity because it has position and time, therefore the two of them better add up to the admissible velocity. So a trajectory has this timing information, and a typical approach in motion planning is to first come up with the path, figure out where you want to be, and then time parameterize that. So then you generate a trajectory. It's not the only way to do it, but it's a simple way to do it. So next thing I want to talk about is a motion profile. So some people, the terminology gets a little muddy, and some people when they say motion profile, they mean trajectory or vice versa. But usually when you hear someone say motion profile, you're actually talking about the shape of the trajectory over time. So you might have a trapezoidal motion profile, where the velocity ramps up and then flatlines and then ramps down. You might have a triangular motion profile on the bottom where you never actually hit a cruising speed, you just go from ramp up straight to ramp down. Or you might have an S-curve profile where you're also varying acceleration very slowly, and so the velocity curve has these really nice smooth sections on it. Another thing that's going to come into play once we're talking about trajectories is feed forward and feedback. So feed forward means you can look at your trajectory and you can say, at 0.1 seconds into the future, how fast should my robot be going? That's a feed forward term because it's something that you've planned ahead of time. There's no sensor involved there. Feedback is like what a PID controller is doing, where it's using a sensor and measuring your difference from your expected state of motion. And it turns out that the combination of these two things is really powerful. Then the last one I want to talk about is forward and inverse kinematics. We're not going to talk a lot about that here, but if you ever go and look at any literature on your own in this topic area, you're going to see these words a lot. And what this basically means is it's a mapping between two different state spaces. So one is the joints of your mechanism. So like if I have a robot arm, it might have two motors and it might have you have a certain angle on the shoulder and a certain angle on the elbow, but at the same time, where's the end effector in like Cartesian space? So you have forward kinematics goes from like your sensor measurements on each joint to like a real world position, and inverse kinematics is the opposite. All right, so now let's get into the meat. So the motion control process. This isn't the only way to do motion control. It's just a very powerful way. We use it a lot on 254 and 971. For example, the 254 robot does some variation of this for all of its driving, all of its turning, and on its elevator system. So basically, the process is figure out where you want to go. So pick a goal point, and maybe that's just you write in autonomous mode, and you say I want to go 10 feet, and then I want to turn right or something. Then you got to figure out a path to get there. In some cases, that's trivial, like well, you're going to go in a straight line. In other cases, you might need to do some interpolation between those points that you'd like to go to. Then you need to figure out a trajectory, which is time parameterize the thing so that you know what velocity you should be going at all times. And then lastly, you have to follow it. And the following part, I think, is actually the most useful one because even if you're not doing the fancy path planning and trajectory generation stuff, you probably still want to be able to follow a straight line or turn in place accurately. So, path planning. So, like I said, path planning is figuring out the sequence of configurations you're going to go through. The 1D case, like if I have an elevator that goes up or down, well, the path from down to up is a straight line. I know where I'm going to be. But in the 2D case, like navigation, it's really, it can be interesting. And optimal path planning is very much an open area of research. You see the graphic on the right from Mobile Garage. I've seen robots actually do that. So the simple way to do like 2D path planning, it's connect the dots basically is what you're doing. You specify this is where I'm starting on the field, this is where I want to drive to, then I want to drive there, and so on and so forth. And there's lots of ways to connect the dots. You could draw straight lines between them, which means you turn in place, then you drive straight, then you turn in place, then you drive straight, then you turn in place, then you drive straight. Or you can fit some sort of curve to it. And what we did in 2014 on 254 was actually a Quintic Spline Fit to those points. And I'll talk a little bit on the next slide about how exactly that works. There are caveats with trying to do this automatically. It gets really hard really fast. As long as you keep it simple, you'll be okay. You can end up with things like strange loops in your path if you try to fit a function and you aren't careful. There's also some code available in FRC repositories to do this. So the 254 code from last year is available. Team 236 actually also put together a really nice like standalone visualization that can do spline fitting. So just real quick, I'm not gonna get too bogged down in this, but the basic idea behind doing a spline fit or any sort of interpolation between these waypoints that you like to go to is you have endpoints defined and you want to try to fit a curve through it. So you want your curve to pass through the first waypoint and you want it to pass through the last waypoint and every waypoint in between. One way to do this is a Hermite spline, which means for each pair of waypoints you create a different function, and all of the pairs are going to all link up so that when you put them all together, you're going to move through all of them smoothly. So you can imagine you have a start position you'd like to be at, some XY coordinate on the field, maybe it's 0, 0 if that's where you turn your robot on. And let's say you want to end somewhere else, a different XY coordinate. And you basically want to fit this equation so that while you're at both of those places for some parameter s. So you have an x spline, you have a y spline, and then you actually have 4 equations here because you have an equation for the position of x with respect to the spline parameter, position of y, and then also for the derivatives. And the derivatives, why is that important? Because that's where you can determine heading, the ratio between them. So that's for cubic spline fit. There's also a Quintic version that does second derivatives too, in case you want constant curvature. There's a lot of literature about this because spline fitting is a problem that's not unique to robot path planning, right? This is you see it a lot in animation. You see it in just even web graphics. And there's other splines that you can look at, like Bezier curves or things like this. And there's some really nice material online to go through what you're actually doing. But the point is, you're creating this continuous sequence of places where you want your mechanism to go through. And just to tease a little bit at advanced path planning, like I said, this is a really cool area of research, and it's one that I do some work in. And you get into things like, well, I have multiple paths that can go from start to goal, and then I'm going over different types of terrain, and there's obstacles, and I have sensors constantly updating my view of the world. And all those problems all boil down together into a really interesting domain. So if you want to do some investigation on that on your own, feel free to bug me either here or online, and I'd be happy to point you at some cool research. All right, so trajectory generation. So we have a path. Maybe your path's just a straight line, maybe it's a spline, doesn't matter. How fast do we traverse it? What are velocities? How do we move the goal as quickly as possible? But how do we do that while respecting constraints? We don't want to tell your robot to go 20 feet per second if it's geared for 10 feet per second. We don't want to try to accelerate instantly because it'll probably flip over. How do we know where and how fast the mechanism should be moving at all points in time? I'll walk through in a series of slides one such approach to solving this problem. It's not the only one. What's really cool about this problem is if you've taken a high school physics course, these equations probably look really familiar. So these are 4 basic kinematic equations, so governing the relationship between velocity, position, and acceleration. And if you haven't taken physics yet, then you can give me just give me a moment. So we know if we're trying to fit the velocities of the robot to the planned path. Do the next slide, actually. We want to generally speed up. This is for a trapezoidal motion profile, by the way. You want to smoothly accelerate, then you want to flatline at a cruise velocity, then you want to smoothly decelerate at the end. So you end up with these 3 different segments. So these are 3 piecewise segments, which in each piece involves a different one of those kinematic equations. So the first step is, if I want to move from x equals 0 to x equals 10 feet away, well, I need to figure out what's the fastest I'm going to be going over this entire period of time. And I know it's one of 2 things. It's either going to be my maximum velocity, or it's going to be the highest velocity that I can reach in the distance I have, right? So if I'm only going a foot away, I'm probably not going to get the full speed before I reach the target. But if it's really far away, I'm probably going to saturate and hit my maximum velocity. So the basic method to do this is we pretend there's no velocity limit, and we look at, well, how fast could we go if I could go infinitely fast? And just as a hint, the distance to accelerate to the cruise velocity and the distance to decelerate back to the ending velocity, well, that better add up to the total distance you have to travel. So then you can figure out your cruise velocity is sort of the max of those different constraints, the maximum reachable velocity and the maximum velocity your robot can do. So next, we know what the maximum velocity is, and now we have to figure out how much distance we're going to cover when we accelerate from our start velocity to their cruise velocity. And there's actually one of those kinematic equations that does this exactly for you. So you can figure out, as I accelerate from where I'm starting to where I need to my maximum velocity, how much distance I cover. Likewise, once you've done that, you do the same thing for the end. So you're going to decelerate from your cruise velocity down to your end velocity. Maybe it's 0, maybe it's not. And you're going to cover a certain amount of distance there too. And then we're just going to need to figure out how long we're at the cruise velocity, which is the difference between how far you need to go minus those other 2 segments. So it's a pretty simple, 3-step approach to generate this profile that has all these nice properties. It does not violate any of the constraints of your robot mechanism because you can figure out what the maximum velocity and maximum safe acceleration are. It is time optimal, so subject to those constraints, this is guaranteed to get you there as fast as possible. And in fact, this will get you there as fast as possible even compared to a bang-bang controller, as long as you pick an acceleration that isn't going to slip your wheels. So what do we have? You have a function where you can look up the desired position, velocity, acceleration of the system for a given time t since the beginning of the motion. So now you basically, it's all smooth sailing from here. I start a motion, I know the next time it comes through my control system loop, I can look up exactly where the robot should be right now. And then I can do some feed forward and feedback stuff with that. I'm just going to real quick mention one alternate approach to do the trajectory generation. And the only reason I want to mention this is if you have Talon, the CAN-enabled Talons, it can actually do this trajectory generation stuff for you. It's extensively documented. And the approach that that the Talon uses is a little bit different, but it ends up with the same answer. So its approach is basically like a signal processing sort of low-pass filter approach. There's a long thread on Chief Delphi where Paul Copioli talks about some of the details of that. There's a link in that thread to a few of the like Excel spreadsheets that you can play with to sort of get the intuition behind it. But just know that if you have a one-dimensional system that you want to try to control smoothly, the Talon can actually do it all for you just over the CAM interface, so you don't have to worry about any of this stuff. All right, real quick. So I talked about a one-dimensional trajectory. So I have this trapezoid over time, which is great and all, but well, what if I have a two-dimensional spline that I'm trying to follow? Well, I can apply this trajectory that I made to that spline just by figuring out the arc length of the spline, and I can say, basically I'm taking this straight line trajectory that I made and I'm bending it to the shape of the spline. And this is exactly what we did in 2014. So we drew out a spline and then sort of discretized and plotted forward in distance along that spline where we should be on that trajectory. So we smoothly accelerated up, and then at the end we came to a halt like you're supposed to. And then one really difficult thing when you're talking about trying to do this trajectory generation for a mobile robot is, well, you have like a very hard control problem because you have non-constant constraints that vary over time, and you have differential constraints. But I'm only going to talk about non-constant constraints. What this basically means is your robot, if you have like a tank drive robot, it can drive a certain speed in a straight line, and it can turn at a certain rate. But if you go in between those two extremes, you can't go full speed straight while full speed turning, because one of the motors needs to go faster than the other, but your outside wheel can only go so fast. So you actually end up with this sort of there's a plot at the bottom where the x-axis is angular velocity and the y-axis is translational velocity. You end up with this diamond-shaped region that those are all the valid velocities that you can command. So how do you munge this thing with the trajectory generation to parameterize a curved path so that you never go too fast? Your outside wheel, you're not telling you to go twice as fast as it actually can. This is actually there's a fairly elegant approach to solve this. And sometimes this is even easier than doing the trapezoid. So this is totally numerical integration based. So we're not dealing with kinematic equations now. We're just dealing with, we're going to move forward through time and figure out what the answer is. So let's say that we have a curved path like at the top. If I have a tank drive robot, I know that my maximum speed that I can drive along that path is inversely proportional to the curvature of that. So at one extreme, going in a straight line, I can go really fast. But if it's a really tight curve, I can actually only go so fast. So you might end up with the dotted red line is showing the maximum velocity that you can be going at any time along that curve. And obviously it's non-constant now. So rather than computing the switching times between this smooth up ramp and then this cruise and then going down at the end, well, we're just going to divide the path up into very small discrete samples and figure out how fast we'd be going in each. So we've computed this maximum velocity thing, and now we can start at the beginning and figure out the maximum velocity that we can go to, that is the minimum of either the maximum velocity in red or the maximum reachable velocity, which is the maximum velocity you can get to from the prior state. So I'm going to leave the mic for just a second. So you start here, and you figure out, I'm going to go a very small distance into the future, and right here, what's the fastest I can go? Well, I can either go that fast, or my active constraint is the maximum reachable velocity from the prior one. So I know if this is 0.01 seconds away, and I have maximum acceleration, well, the fastest I can go is actually this point here. And so on and so forth, until eventually you're going to reach a place where the active constraint is that maximum velocity we computed from the curvature of the path. And at that point, then, well, that's as fast as we can go, and so on and so forth. However, you're going to notice we have a problem here when our maximum velocity goes from high to low. So now we've gone through this whole procedure, and now we're here, and well, then the maximum velocity we can go to at the next stage is really low, but I can't decelerate instantly. This should actually look something like that. So the solution to this is really simple. Well, then after you've done this once, forward, you just do the same thing in reverse. And you just apply your negative maximum acceleration, and you end up chopping this little corner off, and you're left with this trajectory that doesn't violate any of the constraints. It starts and ends at your desired velocity. I use 0 on all these plots, but it doesn't need to be 0. And that's something that your robot can actually do. All right, so I talked at length about how to generate this path and this trajectory that your robot can follow. And it can be, again, it can be a drive train, an elevator, an arm. They all share a lot of commonalities here. But how do you actually follow this thing? So I'm going to turn it over to Tom for a little bit to talk about the approach that we've used extensively on 254 for doing this.
All right. So how many people out there have ever tried to tune a PID controller? How many people enjoyed that process? I feel I'm with you here. So basically, Jared gave a really good intro to kind of motion profiling and figuring out where your robot can move, how fast it can move there, and how to do it. So we kind of have this way of computing, okay, I have this mechanism, whether it's my drive base, or my arm, or my elevator, and I'm here, and I want to move here. Let's compute how to do that nicely. Now we have to actually go and do it. So how many of you have seen 254's robot from either this year or last year in autonomous mode? Has anyone watched the videos? Okay, so when we do turns and drives. And it's a nice smooth turn, it accelerates up, accelerates down, stops right on a dime, and then it drives away. How long do you think it took to tune that system? A couple hours? A couple days? How about like 6 minutes? So basically, and we do this by using feed-forward control. And not a lot of you maybe have heard of this or used it, but I want to talk about why we use it and why it makes your life so much easier. So basically what we do, and what we did last year, and this year we do it on the fly, and all of our code from last year is available on GitHub, and we're going to release our code from this year at the end of the year. So at the end of this year, you'll be able to do on the fly motion profiling and pre-computed motion profiling just by stealing our code. Hopefully you should read it and learn something from it. But the idea is that you'll be able to do it. So what this is the kind of pre-computed way of doing things. So basically you calculate your trajectory, you figure out over time, you basically have a big array, and then each thing in the array is a thing that says, at this point in time, I should be at this position with this velocity and this acceleration, right? Because you know what all those things are. So it's pretty easy, right? Like you grab your set point by looking it up in that array. Then what you do is you take the position that the set point says you should be at, and you subtract your measured position, which is like an encoder value or whatever. I'm not going to talk about the 2D navigation case because that's harder. So basically, you go and you find your set point, and you measure where you are, you find the error, and everything's based on that. So the first thing you want to do is tell your controller what your robot's doing. So if you have a robot that's perfect, right, you should be able to say, compute your trajectory, and just press play. And if the robot doesn't have any friction or anything, it'll always go to the same spot. Unfortunately, that's not the case in the real world. So what we do to kind of fix this, the first thing you do is you look at velocity, right? Because we mostly care about, when you're driving, most of that motion comes from moving at a constant velocity, especially if you're moving a far distance. So the first part of our control loop, before we ever even touch P, I, or D, is velocity control. So you know what velocity you should be moving at. So basically what you do is you take that velocity, you multiply it by a gain, you shove it into your system, and it just starts moving. So KV, versus like KP or KI or KD, that's just another term, and it's a velocity constant. And basically it's just a ratio between your real world velocity that you want to move at and what the motor can actually do. So if you've programmed an FRC robot, you've done like speed controller dot set, right? And like you give it a value between -1 and 1, right? 1 is full, -1 is full reverse. So KV is just a mapping between what the real world of that is and how the motor actually does it. So basically what will happen there is it's hard without the graph, but you'll say, I want to be moving at this velocity over time, and you'll give it that gain, and then it will start moving, but like say you have a really long path, you want to drive 10 feet. It'll slowly lurch up to full speed, and then when you're moving your full speed, right, you'll be applying full power to your motors, so you'll be moving at full speed. And then it'll start to slow down and it will kind of go over its goal. So you'll get, if you look at the graph, you'll have a line that's parallel to your velocity. Like if you want to go velocity here, you'll end up doing that velocity, you'll just end up way past where you want to go. So the next thing you do is you add in acceleration, because we've also calculated what acceleration should be at that point. So you do the same kind of thing. You do kV times your set point velocity, and you do Ka times your set point acceleration, and you just apply that to the motor. And you may be wondering, like, hey Tom, where's the encoder come into this? And like, it just doesn't, right? This is just all pre-computed. You don't need any feedback for this. And this should get you like pretty close. So, yes. We are on feedback control now. Where's the slide? So, okay. Yeah, so the next thing is so now you have a system where you say, I want to move forward, and I'm going to get there by like doing the acceleration and doing the velocity, and you might be able to get within, say you have a drive base, you might be able to get within 3 inches every single time with no encoders, right? But if you put a dead battery in, it's going to go shorter. If you have some stuff stuck in your gearbox, it's going to go a little bit shorter. So how do you account for that? That's where you add your feedback in. That's where you need your encoders. That's where you need your gyro. So at this point, what you do is you basically take that equation you had before, which is kV plus Ka times the velocity set point and the acceleration set point, and then you take the error of where you are, where you expect to be, not where you want to be, where you expect to be at that exact moment. So if you're 1 second in and you're moving and you think you're here, but you're actually here, your error is really small, right? So now you don't need to like have this PID loop where it screams out and then it overshoots and it oscillates, right? You're just trying to track to a nice little moving target. And it turns out because KV and KA are doing almost all of the work, your proportional gain can be very, very low. And most of the time you won't even need derivative renderer for doing first robots. We use a little bit to make everything perfect, but you don't actually even need it. Yeah, and there's a gotcha here. You should subtract out your velocity set point because you want to get the instantaneous error in velocity, not over time.
So one of the part of the gotcha here is if your feed forwards is perfect, your feedback controller should need to do nothing. So if you think about it, your error derivative will be the velocity of the robot. So if you're moving at 2 meters a second, that will be a 2. But you really want that to not contribute any power. So you want to subtract off what you should be moving at, so you'll get 0 power from that term.
Thank you, Austin, for clarifying that. Anyway, so here's how you do the tuning. This is the part that is like, you have all this code, you put it on your robot, now what do? This is the slam your head against the table part. And fortunately, it doesn't have to be. If you give me your robot right now in the pits on the practice field, I can put our code on it, and in 5 minutes I can have it running really, really well just by using pre-canned constants. And it makes sense, right? You've already calculated your maximum acceleration, you've already calculated your maximum velocity. So what should the velocity gain be? What should KV be? It should just be 1 over maximum velocity, right? Because if you want to go full speed, what should you apply to the motor? 100% power, right? If you want to go 50% of T. If you want to go 50% of your maximum velocity, what should you apply to the motor? About 50% power for a linear system. So you could just plug in 1 over max velocity and 1 over max acceleration for your KV and KA, and that's going to get you most of the way there. There's ways to tune it. You can do better or worse, depending on, if you make those bigger or smaller. But for most of the time, that's gonna like get you halfway there. So then you want to do the feedback. basically what you do is you start with all your gains as 0, and you start with KP, because that's the thing that's going to get you most of the way there, right? That's like, my error is 5 inches, I want to apply a bunch of power to get there, right? Just instantaneously. So you basically, what you do is, it's really, really helpful to have graphing tools for this, like on-the-fly graphing tools. So you either want to use like the smart dashboard stuff, and you want to plot your set point versus your measured robot state over time. We have a web dashboard that we built that will be in our code that we're releasing, so you can feel free to use that as well. Or you can record the values and then put them in Excel. Doesn't matter. Any way that you can see your set point moving and your robot moving is going to help. So basically what you want to do is you just want to ratchet up KP to get that. So if you see you're trailing behind your set point or trailing ahead of your set point or going ahead, ratchet up KP so it kind of tracks until it starts to oscillate a little bit and then back off until it's nice and smooth. And that gets you pretty much close enough. And then if you have steady state error, you can increase KI. If you're like here, and you want to be here, and you can't quite get there, KI will get you there. And if you're overshooting a ton, you could add D to dampen it out. But the cool thing is the feed forward does like all the heavy lifting, right? Because we've modeled this. We know how fast it's supposed to go. We know how much power we need to give it. So like the PI and D terms do very little. And most of the time, as I said, KP is the only thing you need. That's about it.
All right, so we talked about how to generate paths and trajectories and how to follow them. Probably about 5 more minutes and we'll open it up to questions, but I just want to talk real quick about some best practices. There's some practical matters that need to be taken care of before you can go and actually do this stuff effectively. So the first thing is, I talked about dead reckoning and bang bang and then PID and then motion profiling. There's a time and a place for all of those things. Bang bang control has plenty of uses in first, so does dead reckoning. You don't want to put a sensor on your intake or something, you can just run it at full power. Try the simplest thing first, and a surprising amount of the time, the simplest thing is going to work. The 254 elevator this year with two independent carriages that can stack together is actually a lot of the time running a bang bang control loop. Some of the times it's doing motion profiling. But so another thing is mechanical robustness is important, especially because typically when you're writing code and you're deploying it the first time, you don't have a lot of confidence in the code. That happens to the best of us. And what is really frustrating is when you're trying to debug software and hardware issues at the same time. So applying code on a rock-solid gearbox and mechanism is 1,000 times easier than doing it on one that is going to fall apart on you for a lot of reasons. Another reason is anytime you have a mechanism with a limited range of travel, like an arm or an elevator, you're going to hit the hard stops at some point. You're going to do something wrong or put something in backwards, or you'll have a bug, and you're going to find out what happens when your system goes to its end of travel. So designing your mechanism such that it's not going to totally destroy itself if your arm goes all the way up against its limit. That's definitely a best practice. Tom was talking about a tuning process, and a big part of that is visualization. If you can't see a line plot of what your robot's doing over time, it's very, very difficult to actually debug it. Even just sitting there looking at your mechanism moving, your eye is picking up on some things, but it's going to miss some cues, some information that's really, really useful. And Smart Dashboard is one great way to do this, or the LabVIEW dashboard, or you can write something on your own. We actually have a HTTP server running on our robot that serves JavaScript that does the visualization for us. Good sensing makes everything easier. Again, this gets into the mechanical robustness thing. Encoders are great, gyros are great. These work well in FRC. Compasses are pretty awful in FRC. They're very slow to respond. You're going to really get frustrated if you're trying to do feedback control with that. Cameras are particularly nasty because there's a really long delay between when an image is taken and when you're actually going to see it in your code. I'll talk a little bit about how to do that in a sec. Precise timing. Actually, in just a sec, I'll talk more at length about timing. Linearity. So linearity used to be a big problem at first, because it used to be with the older Victor speed controllers, you tell it to go 50% power, and it would actually apply like 40% voltage to the motor. And then once you got to 80% power, it's giving almost 100% voltage to the motor. It was really nonlinear. And all these control methods, PID, the motion profiling, makes the assumption that the underlying system is linear. So if you tell it to go 50%, it does 50%, modulo, some small error. So linearity is very, very important. And lastly, just to plug the Talon, the CAN Talon, we didn't actually use them on our robot this year, just because we're still feeling out the technology, but a lot of other teams have, and it's really powerful, and it can, again, do a lot of this stuff for you for free. Just a real quick note on timing. So you have these control loops. How fast do you actually run them? 971 actually runs all of their code at 200 hertz. 254, the vast majority of our code runs at 200 hertz. So we do this by setting up a timer task or some sort of thread with a weight in it, and we want it to be called 200 times per second. And why 200? Well, it turns out that is the rate at which most of our speed controllers accept PWI input. So running any faster than that is going to have really diminishing returns. And running slower than that, well, you're going to have a more stair-step-like response out of your motors. So 200 hertz is a sweet spot, and the Robo Rio can do that really easily. One note, if you try to do this in the 2015 version of WPI Lib Java, you'll be really frustrated because they're not actually using the hardware timer on the Robo Rio in their timer task method. So we actually will release this too. We patched WPI Lib to actually use the FPGA timer so that when we say 200 hertz, in other words, call this method every 5 milliseconds, it's actually every 5 milliseconds. Because if they call you at 5 milliseconds, then 10 milliseconds, then all those integral and derivative and trajectory time-based looked up things, they're all going to explode. Monitor your CPU usage, make sure you aren't hitting 100% regularly. If you do that, again, that's going to mess with your timing, the repeatability. And the last one's really important. Even if you take nothing else from this talk, always use a measured delta time unless you're really, really, really confident that you're getting called at the right frequency. Because as long as, if I have an integral or derivative term and there's some jitter in the timing, if I can at least measure it and apply it, so I multiply the integral of error times the right delta t, that'll at least get back some of that. Yeah, so I'm not going to talk through this too much right now, but this is just connecting all the blocks that we talked about. This is how our drivetrain worked on 254 last year. This is there's a few different ways to do coordinated motion. So if you have multiple jaws on your claw that need to move together or something, well, if you're generating a trajectory for where something needs to be at every point in time, well, you can just generate trajectories such that they're always the same distance apart. It gets tricky, and you need to do some of the things that we talked about for like time parameterizing a path where you have these time varying constraints, but that's the basic gist of it. And then lastly, let's say FIRST gives us a game next season where the camera is once again a big part of it. Cheap cameras make poor feedback signals, mostly for timing related reasons. You have this huge delay. It can be on the order of, if you're doing onboard processing, on the order of like 50 milliseconds. If you're doing offboard, it can be like 5 times that. So what works really, really well here is do not try to do a position control loop with the camera as the feedback signal. Instead, go one step earlier in the process and try to figure out, I need to be facing at this angle, and then use other sensors like encoders or gyros to close the loop on the robot. If you do this, you will be far less frustrated with trying to close the loop on vision system. And lastly, we went a little longer than I would have hoped, but we have about 7 minutes left for questions, and we'll be up here for happy to answer them either. Oh yeah, we'll be happy to answer any questions either here throughout the weekend or online on Sheets Delphi or elsewhere. Yeah, Austin's father.
You mentioned that when you turn on the control loop, you'll hit the hard stop sometimes. I've seen some techniques for making that first turn on a lot less thrilling. Can those be described? I think the kid in the yellow can do it.
Yep. At least we'll see where you differ, but at least what we like doing is, when you first time you turn on your control loop, you want to set the maximum speed to something really, really slow, so that your response time can press the E-stop if something's going awry.
Yeah. One of the tricks I like to use is I'll give it like 2 volts out of 12 to work with, and then I'll actually hold on to it sometimes. So you can then let it move and you can feel it and see that it's going to a set point, not running away. And then when you're confident, you can start to add in more power and let it really go.
So you clip the maximum voltage
Yeah.
that's allowed to go through the sensor.
Yeah,
Just
so
before you say sensor set this value, you set it to 0.2.
correct.
Or
So
max limited.
So right where you do the motor right, I'll say, okay, let it do a max of plus or minus 0.1 or whatever.
Okay. Another thing that can be done is decoupling your feedback from your motor so that you can actually simulate, with your feedback, try to simulate your motor and then see actually what your motor is doing before you couple it up. And just for things like getting the polarity right is one of the big things even.
So one of the other things we did on 254, at least this year, is we wrote a kind of off-board physics simulation engine. It's really, really simple, right? You basically just say, like, I have a motor and there's this load attached to it, and we basically like shimmed out all the stuff in WPILib. So like where you make like a Victor class in WPILib, right? And then you can write some code that has like a Victor observer, right? And you can pull the value out of that and shove it into your motor model, and then it spits out where it is. And then you write that into like an encoder setter object, and then like the encoder in your code reads that value out. And then we take our jar that our robot code generates, and we take the simulator and we mash them up and we run them in one thing, and we can run it on our Mac and like watch the graphs move as we like change the set points and stuff. And that was really useful, and we'll also open source that at the end of this year. Questions? Any more questions?
So how would you go about motion profiling a change in altitude? So if a robot has to go up a ramp or something along its path, how would you factor that?
I will let Jared answer that, or Austin.
Yeah, that's the first thing I would try is ignore it and see how it works. Sometimes you can pretend the world is, a two-dimensional manifold that's sort of draped over all these three-dimensional objects, and that'll work well enough. If that doesn't work, doing higher dimensional planning can be tricky. The other thing you can do is if you know that there's going to be an obstacle there, the whole concept of feed forward is if you know something and you think it'll help, tell the controller. Just push it in there. There's a feedback thing that'll deal with anything that you got wrong. But if you know that you need to apply some more power here, well then put it in there. I know on some automotive, like adaptive cruise controls, there's been experiments with putting a forward-looking inclinometer or some sort of vision system to try to anticipate when you're going to go up a curve. All right, another question?
When you were describing the feedback and the feed-forward terms, it almost looked like you implemented them in two different steps. Is that true, or are you implementing them in the same step?
Oh, we implement them in the same step. I just sort of walked through, in the slides, the equation was like if you're doing feed forward only and then feedback only. But then, yeah, we would...
So when you implement the speed, you have the feed-forward term has to be in there as well?
Yeah. We add the two together. And like you were saying, hopefully the feed forward is the vast majority of the work, because it's nice and smooth and isn't, super sensitive to sensor noise or anything like that.
The quality of the sensors that's being used for your feedback terms really play a part in here.
Absolutely.
So do you do any signal conditioning on your encoders or gyros, or what kind of gyros and encoders do you use in your device?
Austin can talk more about the gyros. For encoders, we tend to just use US digital off-the-shelf encoders and don't do any conditioning whatsoever.
We like to make sure we have high count encoders, pretty much as high as we can get them reasonably. And then we've gone to extra work to do a custom board with a very nice analog devices gyro, just to get the extra resolution. And it's been very useful this year.
All right, well, thanks for your attention. If there's any more questions, feel free to come up and talk to us.